Yeah. So there are two things to check. First is that this is an isomorphism. So this is an isomorphism, and the second thing is that this one is non-zero. Yeah. So the claim is M tensor D. This is an isomorphism, and then I'll have to also check that this is non-zero. Yeah. So why is this an isomorphism? Well, this is where the fact that h of d has finite length comes in. So it's enough to check, enough to prove that each morphism in the link is an isomorphism. So it's enough to prove this. This is an isomorphism. To prove this, so the way the Čech complex is constructed, there is an exact sequence of complexes, which is of this form. So maybe I should try to get this carefully. So one has n xn plus 1, xn and xn minus 1. So one has an exact sequence of complexes just from the construction, and this gives you a long exact sequence in homology. So this is up to suspension. Suspensions are not so important. So this gives you a sequence like this. And again, going back to the same one. See, if you have an exact sequence of differential modules, you end up getting what are called exact triangles, not long exact sequences, because there's no degree. So it's enough to prove this is 0. But you see, the way things work, this is, you can localize this side instead. And because D had no homology, when you localize any element, this ends up having 0 homology, and it's not a trivial result to show that this is actually 0. This is where you have to use the fact that D is a direct summand of a differential module with a flag. So it has this, it's what I said, a cofibrant object, so it has this lifting property. It behaves like a complex of perfect projective modules. So if you have a complex of projective modules with no homology, that's contractible. Yeah? The same sort of result has to be proved. So you have a differential module which has no, so this is a differential module which has no homology, because this one is just h of d localized at xn plus 1. This had finite length, so this is 0. In fact, it's no longer even a complex of projectives, it's a complex of flat modules with no homology, but it's a bounded complex of flat modules. It's a differential module whose underlying module is flat. And using, as I said, the fact that it's a direct summand of something with a flag, you can show that the homology being 0 is preserved under tensor products. So that's a non-trivial calculation here. So this turns out to be 0. So this turns out to be an isomorphism. So each link in this chain is an isomorphism, so the composite is an isomorphism. Yeah. So this is where it would really be nice to have a homological algebra over differential modules worked out properly, and that's what's done in this work with Christensen and Piepmeier. Okay, there's still left. This is still left, and that too turns out to be an interesting challenge or an exercise. So what you need, the last step in the proof, and maybe is appropriate in this audience. So the last step in the proof is a version of the Nakayama law. But for differential modules. Yeah. So we have to prove that the tensor product, the homology of the tensor product is non-zero. If you're dealing with complexes, it's trivial because you can look at the last homology. Basically, it boils down to the standard Nakayama's lemma that if you have a finitely generated module and a module that's not divisible, then the tensor product is non-zero. But it gets a little harder with the differential case. And what you need is the following. So again, let me be precise. So if you have a differential module, D, a differential module that is a retract of, or that is a direct summand of a differential module is a flag. So as I said, this is really the business of cofibrillant object. And so let M be a R module and H of D not equal to 0 and finitely generated. So of course you always need finite generation of some sort for Nakayama's lemma. And finitely generated. The homology is non-zero and finitely generated. Then for N not equal to M, something that's non-divisible, the homology is non-zero. Exactly what you want here. Exactly the hypothesis of this. So this again, this calls for a proof. It's not immediate or obvious for differential modules. So this, if you accept this, this completes the proof of the class inequality, because finally we have checked that the Gauss lemma applies. Okay, so this completes the proof of the class inequality, and this is where I want to end today, but maybe I should, before I end, let me give you a simple example to show that this is something, again, that calls for a proof by leaving you with the following example. So if you look at the ring x square xy, and I want to take D to be the differential module. So it's again just the ring itself and multiplication by x. X square is 0, so that gives you a differential module. So note that the homology of D is non-zero. For example, x times y, the kernel of multiplication by x is x times y, whereas the image is just x. So the homology is non-zero. However, if you look at